Neutralisation. What is neutralisation? Well, let's start with the pH scale. The pH scale is used to rank and measure substances' acidity or basicity, how basic it is. It ranges from 0 to 14, where 7 is neutral, anything below 7 is considered acidic, and anything above 7 is considered basic. Indicators. pH indicators exist as liquid dyes and dye-infused paper strips. They are added to various solutions to determine the pH values of those solutions. What are some well-known indicators? First, universal indicator. It goes from a red to yellow to green to blue to purple, much like a rainbow. Second, litmus paper. Goes from a red to purple to blue. Phenolphthalein. It is colourless unless added to a very strong base. Methyl orange is red only when added to a very strong acid. The rest of the time, it's yellow. Bromothymol blue is yellow, then green, then blue. In this video, we'll be covering the basics of neutralisation reactions with an example, and in the end of this video, 2 choices if you would like to see more. These reactions will all be tested using butterfly pea flowers as a pH indicator, which ranges from a pinky orange when in an acidic solution, blue when in a neutral solution, and teal when in a basic solution. Neutralisation. A neutralisation reaction, also known as an acid-base reaction, is a chemical process wherein an acid and a base react together to produce water and a salt. The high pH of the base interacts with the low pH of the acid, effectively cancelling each other out to form a neutral product. The general equation for a neutralisation reaction looks like this. An acid plus a base becomes water and a salt. Acid-carbonate reactions can also be described as neutralisation reactions, as a carbonate is always a base, which neutralises the acid with which it's reacting with. The general equation for an acid-carbonate reaction looks like this. An acid plus a carbonate becomes water and a salt and carbon dioxide gas. This shows that the result is very similar. The only difference is the additional formation of carbon dioxide gas from the carbonate. Therefore, acid-carbonate reactions can also be neutralisation reactions, but neutralisation reactions cannot be acid-carbonate reactions. For this reason, the common reaction between vinegar, which is actually acetic acid, and baking soda, or sodium bicarbonate, can be described as both a neutralisation and acid-carbonate reaction. When vinegar, aka acetic acid, and bicarb, aka sodium bicarbonate, are mixed, they cause an acid-carbonate reaction as well as a neutralisation reaction, because vinegar is an acid and sodium bicarbonate is a base. This reaction produces water, carbon dioxide gas, and sodium acetate. We can see this in the word and chemical equation. Acetic acid plus sodium bicarbonate becomes water plus carbon dioxide plus sodium acetate. CH3COOH plus NaHCO3 becomes CH3COONA plus H2O plus CO2. In reality, this equation looks quite different. The acetic acid and sodium bicarbonate react together to form sodium acetate and carbonic acid, HCO3. However, carbonic acid is highly unstable and very quickly decomposes to form water and carbon dioxide gas. Here we can see I've set up 3 glasses with a water and indicator solution. On the left, I'm going to add the vinegar or acetic acid. It's become a pinkish purple. In the second from the left, I'm going to leave it neutral so that we have a comparison. And on the second from the right, I'm going to add sodium bicarbonate, the base. And we can see it turn that deep teal colour. Then I'll pour the acidic solution into the basic solution, and once the bubbling has ceased, we can see the product. And here we can see that the product has gone back from the pink and the green to the neutral blue colour. So, that was all for this quick demonstration of neutralisation. I hope you all found it interesting and learned something new. To see more examples, at the end of this video, click on one of the 3 options to see what happens when a different acid is mixed with the sodium bicarbonate.